Hello everyone, I'm Chunyang Ling from Peking University. I'd like to present our paper Graph Neural Network-based Collaborative Filtering for API Usage Recommendation. This is the outline of my presentation. Nowadays, developers usually reuse APIs provided by external libraries and face the need to find out which APIs should be used for their purpose. To solve this problem, many works on API usage recommendation are proposed to facilitate the process of API reuse. For example, as a developer has written part of the code, the recommender system can use the partial programming context to recommend related APIs and even a similar code snippet from repositories. That would be very useful. Basically, prior works usually take advantage of large-scale client repositories by different clustering methods. For example, Maple and UP-Miner use frequent pattern mining algorithms, while PAM uses a probabilistic model to learn from API call sequences. However, these approaches only use incomplete representations, and many suffer from redundant example problem. Recently, researchers applied the context-aware collaborative filtering recommender system to API recommendation and achieved state-of-the-art performance. The basic idea is to fill the 3D reading matrix, just like in the product recommendation scenario. It finds out potential APIs from similar projects and similar methods. So the key process is to identify potential related projects and methods by feature vectors. However, Focus only uses one hot sparse feature vector and the TF-IDF similarity measure, which is oversimplified and unable to capture holistic relations. In this paper, we formulate this problem in terms of graph-based collaborative filtering. As illustrated in this figure, our graph mainly consists of three types of nodes. Client method nodes U, which is analogous to users in general recommender system. The API nodes I, which is analogous to items. And structure nodes, which is specific in our problem. Structure nodes include classes, packages, and projects that are useful to review software knowledge. The graph consists of two types of relations. First, API call interactions. For example, method U1 calls API I1. Second, the project structure relations. For example, method U1 is a member of class C1 and C1 belongs to the project P1. In fact, we will consider many other client projects which also will use the same library. So we just use the former picture as a simple illustration. Now, let's suppose that a developer is currently writing method U1 in project P1. Our task is to recommend useful APIs for U1 given the partial context. How to use collaborative filtering to do this? Here are some hints. First, we can explore the API call relations such as the paths U1, I1, U2, and I3, and find out that I3 is a useful API. Similarly, we can explore the project structure relations such as U1, C1, U3, and I4. Here we meet the challenge of high-order connectivity. There are many passes that are composed of multi-hop nodes, not just direct labels. And these different kinds of paths have different importance. It's hard to set manually. If we use oversimplified feature vector, it will fail to capture complete high-order structure. To address this issue, we propose to apply graph neural networks to exploit the high-order collaborative signals. Basically, GNNs are deep learning-based methods that aggregates information from the graph structure collectively and update the hidden state of nodes by a weighted sum of their labels. Recently, GNN has been widely used in various graph-related tasks and achieved remarkable results. In this paper, we propose GAPI, a graph-based collaborative filtering approach for API usage recommendation. Here shows the overall pipeline. It mainly consists of 3 parts. First, extracting relations from client source code and builds a unified graph. Second, embedding the graph into the continuous space using neural networks. Third, measuring similarities by the node embeddings to predict API usage. Finally, we can use the trained model for online serving. Here are some details about learning graph representations. It consists of 2 modules. First, encoding the text attribute of a node that is useful to represent its own features. For instance, the method name often reveals the function semantics, so we tokenize the text attributes into a sequence of words, and then use GRUs with attention mechanism to encode them. Second, the graph structural features are captured by the stacked graph convolutional networks. After that, we obtain the graph embedding for each node. Finally, we can measure the similarity between a method U and the API I using their node embeddings, and rank all APIs by their scores. As for model training, we construct the training set as triplets, including a client method U, a positive API I, and a negative API J. We use hinge loss function that encourages the distance between positive samples to be closer than that of negative samples. Here is a concrete example. We can recommend a list of APIs according to the partial context of current working method, and also a similar code example from repository. In the evaluation, we investigate 3 research questions. First, effectiveness of GAPI. Does it outperform the state-of-the-art methods? Second, the model utility of GAPI. Does it help improve the performance? Third, the parameter sensitivity. How does the parameter settings affect its performance? Following focus, we use 3 public available datasets, which are Java projects retrieved from GitHub and Maven Central Repository. This is the statistical information about these datasets. To study whether GAPI is applicable in real-world settings, we simulate the behavior of a developer working at a software project with partial programming context. First, we randomly split the methods in a project into key fonts and conduct cross-validation. Then, for each method Q in the test fold, we keep the first pi API invocations as visible context and the rest as ground truth. We compare GAPI with 2 groups of baselines. First, the state-of-the-art approaches including focus and PAM, which I introduced before. The second group is variants of GAPI that are aimed to study the RQ2 about the model utility. The one variant removes the project structure nodes so that the graph becomes a bipartite graph that only contains the API calls. The other variant removes the word embedding module and only retains ID embeddings for graph node. We use 4 metrics in our evaluation. That is success rate, precision, recall, and MAP that are common metrics for top K ranked list evaluation. As for the effectiveness, here shows the compression results of precision recall curves on 3 datasets. A curve closer to the upper right corner indicates a better accuracy, and the area under the PRC equals to the value of MAP. We can find that GAPI obtains higher precision and recall at the same time, as its PRC is always above other curves. There are some interesting notes about the results. First, GAPI makes more significant improvement in recall because it can find more potential APIs that can be hardly identified by prior works. Second, as the number of projects grows, the precision and recall increases as well, since it is more likely to find similar code snippets by collaborative filtering. In addition, this table shows that GAPI consistently outperforms the baselines on 3 datasets in terms of success rate and MAP metrics. As for module utility, we compare GAPI against its variants. We can see from previous tables and figures that the performance drops in the variants of GAPI, demonstrating that both project structures and word embeddings are helpful for API recommendation. Also note that these 2 variants of GAPI outperforms POCUS, which demonstrate the advantage of our GNN-based collaborative filtering framework. In RQ3, we study the effects of hyperparameters, including the kernel size of graph convolutional layer, DK, and the node embedding size, DE. The experiment result shows that MAP and recall increase with the size of model parameters, but the gain becomes slight as the parameter size grows larger. Meanwhile, the time cost and memory cost also increases significantly, especially for the node embedding size DE. Therefore, considering the trade-off between the effectiveness and efficiency, we set both embedding size and the kernel size to be 64 for all datasets in our experiment. In conclusion, we propose GAPI in this paper, a graph-based collaborative filtering approach for API usage recommendation that mainly includes 3 contributions. First, constructing a unified graph of API core interactions and project structures. Second, incorporating text attributes and high-order representations refined by GNNs. Third, experiment results on large-scale software repositories demonstrate that it is effective and outperforms the state-of-the-art approaches. In the future, we will incorporate richer types of project structural relationships into the graph and apply GAPI to more programming languages and wider datasets. Thanks for your listening.